Hey guys, BuildZoid here, and today this video is getting done. And I'm saying getting done because I've had the notes written up for this video for several months. This video has had more failed retakes than I think in recent history any other video, which doesn't really make a lot of sense because this motherboard's not that special. So let's get to it. The Prestige X570 creation from MSI, and no matter what, I am posting this version. So, except if I accidentally swear. That's like the only thing that definitely isn't making it to the channel. So, first things first, this motherboard, like, the most noteworthy feature of this motherboard is this right here. This rear I/O is just freaking awesome. You've got tons and tons of USB ports, just USB ports for days. You've got 10 gig of Quantia, 1 gig Intel, and then you also have a clear CMOS button, and it looks like this clear CMOS button is recessed a bit into the I/O shield, so that's kind of neat because I have heard from people that they accidentally hit the clear CMOS button. Well, if it's recessed into the I/O shield a bit, much harder to do that, like by accident. So, yeah, though I've personally never done that, so, you know, but apparently people do that, so this might help with that. Though I'm not sure if this is the final version of the rear I/O for this board, because, no, I did rip this off of MSI's website, so this is the final version, because the thing is, the actual board picture right here, this is an engineering sample board, and you can tell it's an engineering sample because it's got all of these debugging headers still on it, so retail boards don't have those. Yeah, so... yeah, pretty, you know, filled out rear I/O. The only thing that's really missing, that you could argue is missing, is that there's no Thunderbolt 3 support there. But say, like, I personally really like this rear I/O. This is like, this is what a rear I/O should look like, in my opinion, on high-end motherboards. So... anyway, moving on from that, other features we have, well, I guess you know, it's noteworthy. We've got a post code, we got a power button, we got a reset button. So all the sort of the bare minimum for test bench usage, we've got that. And of course, the post code, very helpful for troubleshooting, especially if you have a windowed side panel, which is pretty standard on cases these days. We've also got 4 debug LEDs up here, which they're all the same color, so you may as well just use the post code instead, because this will convey far more information than than these will, and it's not like you can tell which one lit up at just like a glance, because they're all the same color and right next to each other. The 24 pin is at a right angle. This is noteworthy because this motherboard is eATX, so it's long, like it's wider than an ATX board. So already, just the PCB of this motherboard itself can cause compatibility issues with cases that have a recessed motherboard tray that aren't designed to take motherboards this wide. But the angle to 24 pin makes that even worse because the plastic of the actual 24 pin connector for the cables is going to end somewhere around here. So the board is really, really wide. Effectively, the board is even wider than the edge of the PCB. So that is definitely something to watch out for when choosing a case for this motherboard, because, yeah, the 24 pin is going to stick out a bit. And I think that might be everything in terms of, like, the more normal features. There's 2 M.2 slots, no, not 3, which is kind of interesting because, like, the Ace and the... Unify, right? Those two boards actually have 3 M.2 slots, and then this is a tier above those, and it's just like, yeah, this only has 2. But anyway, but the thing is, it also does come with an M.2 expansion card, so I guess the logic from MSI there is that if you have this board, you're just going to use the expansion card for your M.2s instead of the actual board itself. Anyway, we've got dual 8-pin power connectors. Each of these, so MSI actually uses the low current variant of the power connector. So that's, like, you can tell because this is like a folded metal pin instead of a solid metal pin. The solid metal pins are good for up to 13 amps if you have 16 gauge cabling on your power supply, which most power supplies don't have. Most power supplies are done in 18 gauge, in which case you're looking at 10 amps per pin pair, so that makes each connector 480 watts. But this variant of the connector is 8.5 amps per pin pair, and that's the connector limit, not the cabling limit, because this is the low current variant, and that's that basically puts each of the connectors at 384 watts each. And so this is more like a single 8-pin is more than enough power to power even like a fully maxed out overclock on a 3950X. But the extra power connector here is actually kind of useful because MSI, what they do on their boards is they actually use the 8-pin power connectors to provide power to the PCIe slots. Now, I'm not entirely sure if it's extra power or if it's all of the power. I'd like it to, like, personally, I think it would be much cleverer to have it as extra power to the PCIe slots, because normally the issue is, like, let's say, like, with a board like this, let's say you install 3 RX 480 reference cards. Just, they're the best example of a high PCIe slot power consumption GPU that I can think of. There's probably other cards that would fall into that category as well. This is just the most prominent one. So yeah, you stick to 3 RX 480s in here. Normally you'd blow up the 24 pin. Not an issue when you pull the power from the 8 pins up here, but it's just like to me it would make sense having, say, the 24 pin powering like this PCIe slot and maybe one more, and then just having one slot actually connected to the the CPU power connectors. But I doubt they've really done anything that elaborate with it. Yeah. So that's kind of the thing. I think they're literally just all of the power is provided by the CPU power connectors, and I'll leave a comment under the video if I get more details from MSI about how they actually do their power distribution, because normally, like normal motherboard vendors, just use the 24 pin and the 8 pins are exclusively for the CPU. But anyway, it does mean that if you wanted to fully populate all of the PCIe slots on this motherboard, you should, well, it depends on the CPU you have, right? Like if you're running a 3950X and like really hammering it with an overclock, then you'd actually want to plug in like an 8 pin and a 4 pin. And you can plug a 4 pin into an 8 pin. Like the connector's specifically designed that way. Like you can stick a 4 pin into an 8 pin, which is why the 4 pin connector is kind of dumb, because it's just like, well, if your power supply has a 4 pin, that still fits in an 8 pin. So you don't need, like, yeah. Anyway, so yeah, I just think it would be neat if MSI actually, like, if their motherboards explain that, hey, if you want to use a lot of PCIe devices, you should probably plug in both of your 8 pins. But so the thing is also, on most other motherboards, I say that, dual 8 pins like this is completely utterly pointless, because on most other motherboards, it only powers the CPU, and just like the CPU is not going to pull even that, right? So a single 8 pin is more than enough for the CPU on its own. But with a motherboard like this, where the 8 pins also power the PCIe slots, having an extra one is a reasonable design decision. So yeah. It's just, I really wish there was some clarification in any of the documentation for MSI motherboards that they do this. Because the way I found out that this is a thing is somebody dropped a comment on one of my videos where they're like, oh yeah, the 8 pins power the PCIe slots, and I tried to validate, like verify that with looking through the manuals, didn't find anything. So what I ended up doing was I ended up plugging in plugging a motherboard in and using a multimeter to check where the 12-volt power for the various PCIe cards, and then had a GPU plugged in, and I would check where the PCIe slot was connected to, like where the card's PCIe slot 12-volt power was connected to. I'm not sure why I'm going into this much detail. You probably don't care. The one thing that's kind of missing in terms of features on this motherboard, in my opinion, is BIOS flashback. Or dual BIOS. Really, any kind of BIOS recovery functionality is just non-existent on this motherboard, which doesn't really make a ton of sense to me, because it's a $500 board, and the thing is, BIOS flashback can be used to recover from bad BIOS flashes. So if you like screw up a BIOS flash because the power goes out mid flash, you can actually recover that with BIOS flashback a lot of the time. Yeah, this motherboard doesn't have that. It also doesn't have dual BIOS, and this just doesn't make any sense to me, because it's just like the Meg Ace, which is $350 instead of $500, has BIOS flashback. Why doesn't the $500 board have BIOS flashback? Just like, or dual BIOS, like either is fine, or better, have both, right? Do what Gigabyte does, have both. Because the thing is, BIOS chips are cheap, and the BIOS flashback functionality, like, I have to assume it's really cheap, because you can get B450 boards with it from MSI. So yeah, it's just like this board not having BIOS flashback is just a great big why? It's not a huge issue, but like, I think on a motherboard this expensive, it just should be there. Like, it just should be there. The thing is, you also don't really have a ton of options in terms of, well, I'm not sure. Like, from like, if you want this many USB ports in the rear I/O, like, there's not that many options. But at the same time, it's like, if you want 10 gig, the ASRock Creator exists, and I do believe that does have BIOS flashback. So it's kind of like you need to compare the features of the various motherboards at the various price points to make up your mind. Like, honestly, the highlight feature for this motherboard is the 10 gig, and there's other motherboards that do that, and you can of course buy 10 gig expansion cards as well. So Yeah, but you might not want to waste your PCIe slots. So there's too many things to consider in that direction. So anyway, I just think it's dumb that this doesn't have BIOS flashback, because it's a $500 board. It should have basically everything as far as I'm concerned. That's just kind of my outlook on that. So with that out of the way, let's talk about the power delivery. And the power delivery is pretty, it's pretty standard. It's really overkill for the platform, but nonetheless pretty standard. So you've got a 14-phase Vcore. And I don't know why I decided to write out the full set, 14 phases, because I should have just written out pH or something. But anyway, then next to that, we've got a 2-phase SoC. And the controller here is an IR35201. So naturally, this VRM, you can't actually get a 14 plus 2-phase configuration out of a 35201 without the use of doublers, because this controller only goes up to 8 phases total. Here it's running as a 7+1, and then there's ×2 on each of those, and I really should that's not a nice notation, but whatever. On the back of the board, we get the ×2 components, also known as doublers. So that's all of these chips right here, and there, and also here. There's a lot of them here. So yeah, and these are all IR3599s. And these can double, they can quadruple, they cannot current balance themselves, but the international rectifier controllers like the 35201 and various other controllers from IR are smart enough to actually distinguish between 2 phases even through a doubler. Not all controllers can do that, so they can actually current balance the entire VRM as if the doubler wasn't really, as if the controller actually had 14 phases. Now, the downside to using the doublers is that they do add a little bit of delay to your PWM signals. However, in my testing with Z390 motherboards, the amount of delay this adds is irrelevant, because the Z390 Dark, which uses a whole bunch of doublers, is the best performing motherboard I've tested so far. So yeah, as far as I'm concerned, it's just you can use as many doublers as you like, just, you have to design around them. That's kind of the thing. So, yeah, I really don't see an issue with using the doublers here. It really just depends on the rest of the VRM design, and as far as the transient response goes, it's just it depends on the rest of the VRM. And the thing is, you can't eyeball transient response performance, unfortunately, because it's too it's way too complex, because it depends on what inductors you use, what kind of power stages you use, your controller firmware, your doublers, your capacitor configuration behind the socket, on the output of the VRM, then the actual power plane itself, how much cross-section does the power plane have, how much stitching does the power plane have, and it's just it is way too complicated to basically go and look at a motherboard and go yeah, this has good transient response with certainty. I would doubt that this would have transient response problems. And I do have the X570 Unify, which is a very similar VRM design to this, since that's a 12-phase, not it's basically this minus 2 phases. So I guess I can test that, and if that turns out to perform just fine, then it's just well, this will perform just as well, right? Because, well, you never know. You never know. It is sometimes possible that the more expensive board is actually a step backwards instead of a step forwards. But I'd be very surprised if that was the case here. Let's just put it that way. But I'm not saying it's impossible. I'd just be surprised. So yeah, that's the control scheme of the VRM. So we do have a 14-phase, though it's not at this point you could have a better implementation of a 14-phase by just using the Infineon XDP E132G5C, which can do 16 phases all on its own. But still, as far as there's I don't see a problem with doing it this way. It really depends on just the rest of the VRM design as well for the the performance end result really depends on more than just what components are used, or well, it depends on what components are used and how you use them. There. So anyway, that's the control scheme. Moving on to the power stages, we've got IR3555s. So it's not 5, yeah, 3555. So those are 60 amp POW IR stages. They're they offer current monitoring, temperature monitoring, But it's not quite like the current monitoring isn't quite as accurate as what you'd get out of the, say, like the smart power stages that we see now. And the temperature monitoring, I mean, nobody really cares. Like that's just kind of there. It doesn't need to be that accurate. And then they don't have any of the like advanced protections that smart power stages have. But you know, for a very long time, this was basically as good of a power stage as you were gonna get. So the end result with 14 of them in the Vcore, this VRM is really overkill for the platform. Like so overkill that it doesn't hit peak efficiency until it's well over 200 amps output, which is just like, honestly, if you want peak efficiency out of this VRM on like a 3700, like even a 3950X with a crazy overclock running Prime 95, peak efficiency on this VRM from at least the power stage perspective, because there's also like the inductors have some impact and that kind of thing, but we'll just ignore the inductors because they don't tend to have that. Like they have a lot less impact on the heat dissipation of the VRM than the actual power stages themselves. So we'll just kind of ignore those. But yeah, if you look at it just from a power stages perspective, this VRM has like 4 or 5 too many for the Vcore. Like honestly, you'd want like a 10 phase or an 8 phase even. So depending on how the controller is actually configured, this thing might not be running all of its phases if you have less than a, well, actually, no, it's kind of unlikely because most motherboards will actually run all of their power stages just for the hell of running them because it's like they're there, you may as well use them, right? So yeah, like that's kind of the thing. Like you'll see VRMs drop down to like 1 or 2 phases at idle, but as soon as you load them up, they'll go all the way up to like as many phases as they have. That's just kind of how most of the that's how most of the VRMs I've tested behave. And then there's also VRMs that don't idle at all. They just always run all of the phases, and that's when it's just like, well, that needs that should have some extra configuration put into it. Anyway, so for the operating so for 1.2 volts, just I need to get this video done. So 1.2 volts output, 400 kilohertz switching frequency. Like we're at the point, like I honestly don't know why at this point I don't just have like a little table that pops up with all of the efficiency figures. Because quite frankly, I think that would be just about that would be more effective than what I currently do with writing them all out. Let me know in the comments if you think that would be a better way of dealing with things. But anyway, 100 amps output, you'd be looking at about 12 watts of heat output. So yeah, you shouldn't, like for this current output, you'd probably want like 6 phases, not even 8. 150 amps output, you'd be looking at about 17 watts. So here you might want like 8. That's the thing. This has way too many phases. 200 amps output, it would produce 20 watts of heat. So now we're starting to finally approach the peak of the efficiency curve. And this is also like, so this is all of the different current draws that you might see with a Ryzen 3rd gen CPU. So this is like an 8-core being absolutely hammered by Prime 95. This is like a 16-core being absolutely hammered by Prime 95. The VRM doesn't care. Like here in the sort of like, this is where most people, because here's the thing, at this kind of current draw on a 3950X, the CPU is basically completely uncoolable at that point. So I don't actually expect anybody to realistically run that. And so within the current draws that are actually realistic, like the VRM here does not need a heatsink at all. Like you could honestly run this motherboard just naked like this all day, every day for like several years straight. It wouldn't make a difference. So yeah, like the VRM here is massive overkill. But anyway, so this is what you'd actually see, like, you know, in normal usage. Going past that just for fun, because I don't think like you could run this motherboard on liquid nitrogen, but it's just like you realistically wouldn't, just because it kind of like there's better, like there's cheaper options that would do just as well, right? Like that's the thing. But let's say you did decide to go on liquid nitrogen with this. 300 amps output, this board would produce about 28 watts of heat. 400 amps output, which I think LN2 you'd actually top out around, well, around 300 amps actually. Because the thing is, if you're above 1.5 volts, 300 amps is 450, like is over 450 watts. So yeah. Anyway, 400 amps output, you're going to be looking at about 40 watts of heat. So finally the VRM, like at this point you probably need a heatsink, but you're also on LN2, so it's just like the benchmarks don't last long enough to really need, like your VRM's not going to overheat if, you know, it's producing this much heat for a short period of time. Anyway, 400 amps, 40 watts. Okay, at this point, you know, cooling would actually be useful. Unfortunately, in extreme overclocking, like the benchmarks don't last long enough. It's not like people run Prime 95 on LN2 for an hour, right? Like that's kind of the workload you need to use when, or run a blender render on liquid nitrogen for an hour or 2 hours. Like you need time for the heat to actually build up. And that's ignoring the fact that the PCB tends to, like if you have the CPU at like minus 100, the PCB freezes through. So the VRM will actually be getting cooled through the CPU and the power plane itself. So yeah, that's kind of the thing. It's just like this VRM is just insanely ridiculous overkill. Going up to 500 amps, it would produce about 61 watts of heat. Like this is the kind of VRM that belongs on like an X299 motherboard. Or maybe like, or a Threadripper board. On Threadripper, this would also be totally acceptable. But for X570, this is ridiculous overkill. But it's also a $500 board, and that's kind of the standard for, you know, motherboards that cost $500 come with ridiculous overkill. That's just kind of the norm. Anyway, the SoC VRM is just more 3555, so it's not even worth discussing. Just like, yeah, this is totally overkill as well. All of the capacitors, like these aluminum polymers that we see around the board, those are all Nippon Chemicon capacitors. So that's a different, like normally you see Nichicon capacitors. That's a Japanese brand. Nippon Chemicon is also a Japanese capacitor manufacturer. These are aluminum polymers. They're all rated for 10,000 hours. Yeah, it's you know, standard high-end motherboard stuff. Actually, even standard mid-range motherboard stuff. Like the thing is, like 10,000 hours rated capacitors don't really cost that much. Not compared to even the funny thing is you can't really get these in like high endurance ratings, but yeah, like a low endurance rating one of these costs way more than pretty much any rating of one of those. So yeah, these are fun. So this is obviously just for the memory power delivery, and that doesn't get hot. Like, especially in this area, that doesn't get hot. So that's kind of why, you know, you see more performance-focused capacitors rather than, like, long-term longevity. Though, honestly, even the Vcore VRM here, just like, this will run ice-cold, so you could have gone with these as well. So, yeah. Anyway, you know, we've got kind of, like, well, damn it, where was I going? Okay, well, so that's the capacitors on the board. Let's talk about the memory. So the memory power delivery is a single phase, and interestingly enough, like this is a single phase memory VRM that like MSI uses on basically all of their motherboards. Like you get this same memory VRM on like even a B450 motherboard, you basically get the same thing. Interestingly enough, it is a bit more substantial than what you would get from say Gigabyte for power delivery, because you've got two high side MOSFETs, and these are also nicer high side MOSFETs than what Gigabyte normally uses. And then you've got two low sides in your single phase. And and it's honestly not worth like the thing is, these are MOSFETs that honestly don't like even like if they're used in the V-core of a motherboard, like that's actually a good place to use them, because this is like a 2.8 milliohm RDS on low side, which is like honestly there's a lot of motherboards where if you had 2.8 milliohm RDS on low side MOSFETs, that would be a big upgrade for like the Vcore VRM, and MSI is just like, yeah, we'll just stick that in the memory VRM, right? So yeah, so the memory power delivery is really like overkill, and ultimately when it comes to DDR4 overclocking, the thing is the memory doesn't pull that much power in the first place, and so what's really important is not so much what you do in terms of the memory VRM, but what you do between the CPU socket and the actual DIMM slots. So all of like this, right? And to that extent, we can see that MSI is doing their full ground fill over all of the memory traces on both the top layer and the bottom layer, because this is a 6-layer board, so they have the space to do this, right? So you can see absolutely no memory traces because they're just covering them up with a ground layer. This basically acts as a shield for all of the traces and is meant to improve signal integrity. So that's the idea behind doing that. We've also got the VDDR island down in the center here. So yeah, MSI has been doing this for, like, they do this on all of their X570 motherboards. I'm not sure how much more effective it is than, like, having the traces exposed. And unfortunately, I don't think I'm technically even really allowed. Well, I can think of one example that I'd like to use, but I'm technically not allowed to talk about it. So yeah, anyway, this, as far as I know, this does work. Like, this does actually lead to better memory overclocking capabilities. I just can't talk about how much of an improvement it makes, and I can't really point to any examples of motherboards where you can go from, like, one version that does do this and one version that doesn't do this, and that's, like, the only difference. So, yeah, that kind of makes it hard to show comparisons between that, but anyway, yeah, so MSI is doing the ground fill thing, and they're doing this for all of their X570 boards, so that's kind of that. In terms of the actual memory topology, we're looking at a daisy chain. Well, we're not looking at it because it's covered by a ground fill, but under that ground fill is a daisy chain. And so that basically means that this slot and this memory slot are favored for memory overclocking. Honestly, when it comes to... The funny thing with Ryzen 3rd Gen is just like, as long as you can do 3800 megahertz, it kind of doesn't matter what topology it is. So, because your FCLK is probably going to fall over at around 18, like between 1800 and 1900 megahertz anyway. So, you know, there's no huge advantage to having a memory topology that can push 4 DIMMs to 4000 megahertz because the CPU can't, like, you're going to lose performance anyway because the CPU, you're going to desync your FCLK with the memory. But yeah, so that I guess is the main reason why MSI uses the daisy chain here, because it's just like if you use a 16 gig configuration, this works really well. So basically this favors 2x8, it favors 2x16. 2x32 is a bad idea on the basis of 32 gig memory sticks kind of suck in my experience. But at the same time, I've heard from other people that 4x16 just absolutely, like, CPUs don't like 4x16. It's too much RAM for them. So it's just like, yeah, don't run, like, if you want high memory speeds, don't buy 64 gigs of RAM, I guess. That's the conclusion there. But for 32 gig, like, also, the thing is, the daisy chain here won't have enough of an impact on a 4x8 configuration to really matter. Like, the only thing you shouldn't do with a motherboard that has a daisy chain is just, like, run this slot and this slot populated while not having the other two. Because that leads to, like, that literally can make it impossible to go over, like, 3 gigahertz, like, 3000 megahertz. So, yeah. Anyway, also, I do believe this is the exact same memory topology that you would get on a X570 Meg Ace and also an X570 Unify from MSI. So, you know, if you're, like, there's no point buying this motherboard for having spectacular memory overclocking support because they have cheaper boards with this exact same memory configuration. So you could get those instead. But... yeah, it's also not a bad memory. Like, the memory topology here is definitely not bad because the Ace and the Unify are both very capable in terms of memory overclocking. So I think that covers everything, right? We've talked about the Vcore VRM, SoC VRM, memory VRM, memory topology, efficiency, rear IO, yep, various features around the board. So it's kind of that. I like, so out of MSI's entire X570 lineup, I kind of like the Creation because it kind of has the most features and the most connectivity options, right? You've got tons of USB ports, you've got the 10 gig LAN, you've got the clear CMOS button on the rear IO. At the same time, I just feel like MSI's X570 motherboard lineup in general is a bit weird. Like, some of the boards, like this not having BIOS flashback is just like, why? It's a $500 board. Where's the bloody BIOS flashback? Like, seriously, guys, what happened? And then similarly, it's just like, well, and then there's, of course, things like this postcode's in the wrong bloody place. Like, it should really not be down there, because if you have if you have a full-length PCIe card, like, it's going to get covered up. So, not really a fan of that. But it's definitely, like... you know, other than those minor issues, in my opinion, with this board, and the fact that it's $500 freaking dollars, it's a nice board, but it is really, really expensive. So, yeah, that's it's kind of that. So, is there anything on the back that I might have missed? No, not really. So, yeah, that's it for the video. Thank you to, well, actually, thanks to MSI for providing the pictures of the board. And so, wait. How do I do... Man, I haven't shot a video in so long, I've already managed to forget how to do an outro. So, here we go. Thanks for watching. Like, share, subscribe. Leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I do have a Patreon. There's a link to that down in the description if you'd like to support me through that. And then, what else is there? Right, I have a Teespring. There's, like, shirts and stickers and posters there, like AHOC merch. So if you'd like to support me through that instead of Patreon, because, I don't know, well, whatever, like, you want to use that instead, There's a link to that down in the description below as well. I know, incredible, right? Where else would it be? And yeah, if you'd support me through that, that would be great as well. And whoa, this video somehow managed to not be over 30 minutes, except for the part where I'm not going to hit the stop button until it is over 30. Except I'm going to hit the stop button now, because that's the end of the video. So thanks for watching, and goodbye.